In this video, we're going to look at some applications involving quadratic functions again. We're going to take a look at a couple of these applications, and in both applications, they're going to ask for max and minimum value of some quadratic function in context of the word problems. Before I move away from this page, just want to remind that the case where the parabola opens upward, remember the graph of a quadratic function is called a parabola. So here's the case where the parabola opens upward, and when it does, the vertex, which is the low point, it's going to be the minimum in this case. Notice there is a minimum. Now the minimum value of the function is what f of x is, not x. X is where you will find it. This is where it's going to happen. But the value is f of x. So the minimum of the function at this point is f of x at the low point. If the parabola opens downward, then the vertex is going to be a maximum, and the maximum is going to be at f of x again. So we're just going to keep these two things in mind. And with that, I'm just going to show you the page of the exercises, so you see where I'm getting these exercises from. These are on page 754 of your textbook. And I believe you're doing exercises number 13 and number 11. So 11 and 13 are the ones that you're doing. Okay, and there you have it. Number 11 is up here. This is number 11. And then number 13 is a couple of problems down below it. There you go. This is number 13. Again, you're doing numbers 11 and 13, both of these exercises. Okay, so with that, there are no formulas to tell you other than what we said earlier, that the max or minimum of the quadratic function occurs at the vertex. So with that, we're actually going to go to our notebook and we're going to start this problem. So we're going to begin with exercise number 12. Okay, in exercise number 12, furniture design. So let me bring this exercise up, and there you go, so you can see a little better now. I'm going to move this one away because this is the next exercise we're going to look at. We don't need that for now. And what else do I need? Let me throw in a ruler here, and just to make you look so it's easier on your eyes, let's kind of color the notebook here. Hopefully you like the color. Okay, so let's take a look at this exercise and see how we're going to model this as a quadratic function. The question reads, a furniture builder is designing a rectangular end table with a perimeter of 128 inches. What dimensions will yield the maximum area? Okay, so we want to know what dimensions will yield the maximum area. Now, for this one, let's take a look at and see how this is going to work. Okay, my pen was inactive for the moment. Now it's working. Okay, so here's what we're going to write down. The only known quantity is really what we are given is 128 inches. Of course, we were told that this is a rectangular end table. So if I draw my rectangle here, and since I don't know exactly what the dimensions are, I'm just going to actually draw a rectangle here. That's my rectangle end table. Now, this end table is going to have, let's say, length and width, right? I'm going to call the length to be L, the width to be W. And of course, the surface area is the area that you see here in this shading. So right now, the area as a function of W and L is going to be width times length. We're told the perimeter P of this table is going to be 128 inches. Now remember, the perimeter of a rectangle is going to be the sum of all sides. So that means 2W plus 2L equals 128. I can divide both sides by 2 to just bring the numbers down a bit, and that's going to be that. Okay, now if you note here, the area I'm using this notation, W comma L. What I'm saying here is this. That's not a point. I'm just saying that the area is a function of two things. Okay, it's a function of width and length. That's all that means. And you can see W and L on the right side. Now, in order for us to work everything like the way we have, we need to have either just W or just L. So we have a function of one variable. Right now there are two variables. So what I can do is the following. In this equation for the perimeter, I can solve for L. So isolate L. That means I can subtract W from both sides, right? And there you have it. So I'm going to rewrite now area A as a function of just W. You see that? We usually write f of x. So f is a function. The function here is the area function. And instead of variable x, we have variable W, the width. So I'm going to write my equation W times L, but then L is 64 minus W. And distribute W, I get 64W negative W squared. So note here, we have a quadratic function in W. Now, because this is a quadratic function, and the coefficient on the square term W, that's negative 1, right? Remember, this is like negative 1 here. This acts as your A. A is less than 0, so the parabola is going to open downward. That means the vertex, since parabola opens downward, the vertex in this exercise is max. That means the maximum occurs at vertex, the maximum width that is. Let me move this one out of our way, out of line of sight. Okay, that's away from our line of sight now. Okay, so in other words, now all I need to do now is to find the coordinates of the vertex. So I'm just going to write now W equal negative b over 2a, right? Remember the formula we had for the vertex, and that's going to be negative. B is 64. Remember, b is the coefficient on the variable, not the squared, but the variable to the first degree. So it's not going to be negative 1. It's going to be 64. This is kind of out of order. Usually we write the square term first, then this one second. So please note that. And a is the coefficient on the squared, which is negative 1. And this will make it 32. Positive 32, that is. Okay, and because, again, the vertex is max here, so this would be the maximum width, W. And that would be the dimension of the width. So width is 32 inches. And plugging for 32 in here, we get the length. Length should be 64 minus 32, or 32 inches also. The units on these are inches, the units of measurements. So length and width turn out to be the same. In other words, this rectangular end table actually going to be a square, isn't it? Because length and width are equal. So this is going to be a 32 by 32 end table. And the area at 32 is going to be 32 times 32, length times width. And that's going to make it 1,024. And that's going to be the area in squared inches. And we have the answer to this exercise. So the maximum area is 1,024 square inches. And that's when the length and width are the same size, 32 inches each. And we are done with this exercise. Just an application of max and minimum with a quadratic function. Our next exercise is going to be, or this will be our last one, is actually exercise number 14. So let me now bring this one up to a little closer to where we can see it, and then let me enlarge it. And here you go again. This one, hopefully you can see this better. Okay, you're doing exercise 13, which is very similar to this one. Now in exercise number 14, here we have garden design. Ginger is fencing in a rectangular garden using the side of her house as one side of the rectangle. So in other words, this is right here. That's the side of the house she's going to use as the side of the rectangle. So in other words, because she's using the side of her house, she does not need any material for that, right? It's probably stucco, and it's just going to be flush against the side of the house. So no material will be used there in order to fence this garden. The question reads, what is the maximum area that she can enclose with 40 feet of fence? What should the dimension of the garden be in order to yield this area? Okay, so let me again label this rectangular garden. So that's going to be W. Maybe not a good choice for color here because it's green already. Here we go, W and W, and call this length. Okay, so note now we don't have two lengths. Remember, the side of the house is going to serve as one side of the rectangular garden. So there are two widths and one length. Okay, and that's going to help us formulate the perimeter. Therefore, the perimeter of that garden is going to be 2W plus L, not 2L, right? Because the side of the house is the other side of that rectangle. And we are told that she has 40 feet of fence, right? Right in here, she's got 40 feet of fencing. And again, I'm going to solve for L. L is going to be 40 minus 2W, right? So we have solved for L. Now, let's write the area. The area is going to be width times length, true? Now, the length is 40 minus W, so I'm just going to replace L with 40 minus 2W, 40 minus 2W. And then we're going to distribute, we're going to get 40W negative 2W squared. And again, just like the previous problem, number 12, A is going to be this number. This is what A is. That's A. And this is actually B. Okay, A is the coefficient on the squared. So A is negative 2, B is 40. The parabola A is less than 0, so the parabola again opens downward. That means the vertex is a max. So the maximum area occurs at the vertex. And now we can actually solve for the vertex. If I do negative b over 2a, that would be the h component of the vertex. That's going to be negative of 40. Remember, b is 40 divided by twice a is negative 2, and that makes it 10. Okay, and this would be actually what we just found here is w, 10 feet. So the width of that, the rectangular garden, should be 10 feet. And when the width is 10 feet, remember, we're going to back substitute right in here and solve for L. So L is going to be 40 negative twice times 10, and that's going to be 40 minus 20, or 20 feet. Therefore, we found the length to be 20 feet, and those are the dimensions of the garden. It's going to be a 10 by 20. And the max area is going to be A equals width times length. Length at that point, the width is 10, length is 20, and that's going to give it 200 square feet garden. And there you have it, the second example. Hopefully this is going to help you do yours. You're doing number 13 again, which is very similar to this one. And with that, we are done with this video also. We'll see you in the next one.